definitions in the one-dimensional dynamics, and as we know, the periodic Fadou components can be classified as following 6 types. There are attracting basins, parabolic basins, super attracting basins, and the Baker domains, the Siegel disks, and the Herman rings. So to talk today, we'll focus on the later 2 types of periodic Fadou components, Siegel disks and the Herman rings. Suppose f is a meromorphic function. It is a rational of a degree at least 2 or transcendental, and the Herman ring is a periodic Fadou component, which is homomorphically isomorphic to some annulus, and the restriction of the map or some iterate of this map and this Fadou components is homomorphically conjugate to an irrational rotation. If the annulus is replaced by a disk, then this periodic Fadou component is a Siegel disk. So the dynamics in Herman rings and the Siegel disks are very simple because they are conjugate to the irrational rotation. For Herman rings, we know that the n-type functions cannot have them because of the maximum modulus principle. And as far as we know, there are 2 knowing methods for constructing Herman rings. Let us first record the first method for constructing Herman rings. We first induce some properties of irrational numbers. For every irrational number alpha, we can write alpha as its continued fraction expansion, a1, a2, an. And the nth convergent, the Pn over Qn, converges to alpha is exponentially fast. What is the Duffanto number of all the nests or equal to kappa? It is defined as the all alpha such that it has some estimate of its distance to all rational numbers. We write the precise definition here. And it says there exists some epsilon greater than 0 such that the distance between alpha and any rational number is greater than epsilon over q to the kappa. And we state some basic properties. The D2, that means kappa equals 2. D2 has measure 0, and every irrational number in D2 is called the bounded type. That means the continued fraction expansion integers has an up bound, and the intersection of all D kappa with kappa greater than 2 has a full measure. And there is a characterization of another characterization of Duffanto numbers. Duffanto numbers D. It is the union of all D kappa with kappa greater or equal to 2, and it is equivalent to this inequality. The supreme of log q n plus 1 over log q n less than is finite. And the Brugiano number is defined as odd alpha such that the sum of all log qn plus 1 over qn is convergent. And there is there is a very simple fact. Every Delphi number is regional. So one can, if the irrational number satisfy this condition, then it is very easy to check it must satisfy this condition. Okay, and then we can state the Arnold's result. Suppose theta is a Delphi number and sigma is a number greater than 1, then there exists a epsilon, positive number epsilon, such that if F is a homomorphism defined from the unit circle to itself with rotational number theta, and F can be extended analytically and uniformly to the annulus, which is a neighborhood of the unit circle. And it also satisfies, it is sufficiently close to the rigid rotation, and the arrow is bounded by epsilon. If F satisfies these two conditions, then F is conformally conjugate to the rigid rotation in a smaller annulus. That means if we can find a holomorphic map F satisfying these two conditions, then we can have a Siegel disk or a Herman ring. But if we make some further summations, then we can obtain a Herman ring. But as far as I know, it is not easy to find such F, because we need to, such F is very close to the rigid rotation, and then it is also required it is uniform in a neighborhood of the unit circle. It also has a rotation number in the Dauphin 2 type. And then later, Herman studied the circle deformation, diffeomorphism, and he introduced a class of irrational numbers H. The H is the set of all irrational numbers theta such that every orientation preserving analytic circle diffeomorphism of rotation number theta is analytically conjugate to the rigid notation. So these conditions seems very hard to verify. If we give some irrational number, then it is hard to check it is belongs to Herman's. It is satisfy Herman's condition. But Herman himself can prove his numbers contains all the Dauphin 2 numbers. So in these things, he can construct a Blaski product BZ equals to E2 2 pi IT z squared z minus 4 and over 1 minus 4z. And the T is choosing such that the rotation number of B on the unit circle belongs to H. Then if T is choosing such that the rotation number belongs to H, then because of the definition of H, we can see every orientation preserving analytic circle diffeomorphism. We can see if we restrict B and the unit circle, then it is indeed orientation preserving analytic circle diffeomorphism, because the critical points of B are far from the unit circle. And therefore, by Herman's definition and the Herman's theorem, we know this B has a Herman ring containing the unit circle, because there is we can prove, we know B has a fixed Fatu component containing the unit circle, and then this Fatu component must be Herman ring or a Siegel disk, but it cannot be a Siegel disk because the zero and the infinity are super attracting fixed point. So the periodic Fatu component of B must cannot be simply connected. It must be a Herman ring. So I think Arnold gave us some basic preparations for the existence of Herman rings, but Herman is the first one to produce specific examples of Herman rings. And in 2002, your course provide an arithmetic characterization of H, and the proof that H is properly contained in the Bruno type, and it properly contains the Dovin numbers. And then this arithmetic characterization allows us to check an irrational number belongs to Herman type or not. Because Herman's condition is very hard to check, but your course give arithmetic characterization. But the characterization is very hard to state here. It is a very complicated the description. Okay, we can give a schematic diagram for the classes of irrational numbers. We can see the D2 is the bounded type numbers. It has a zero measure. The D2 plus, it is the intersection of all D kappa with kappa greater than 2. It has full measure, and it is contained in the Dovin numbers. And the Dovin number is contained in the Herman type. And the Herman type is properly contained in the Bruno type. And your course give a characterization of the complement of Bruno type. We will mention it in a moment. The complement of Bruno type is here, but we will mention it in a moment. Okay, and now we can see some pictures of Herman rings. This is the cubic Blaski product. This example is very classical, and we can see it in Milner's book. The T is choosing such that the rotation number and the unit circle equals to the golden mean. And we know the golden mean is of bounded type, and it's of course it is still Dovin number, and it's of course is Herman number. So this map has a Herman ring surrounding the unit circle, and we mark this Herman ring green like this, and the other yellow part I iterate eventually onto this fixed Fatu component, and the rest place belongs to super attracting basis of 0 and the infinity. The next example is transcendental holomorphic functions defined from the puncture plane to itself. It can be written as E2. It written as E2 2 pi it times g to the e to the 1/4 and times g minus 1 over z. And actually, if at this place there is a parameter, it write as a over 2. If a belongs to the interval from 0 to 1, then this map is a homomorphism defined from the unit circle to itself. So here we choose the parameter a equals to 1/2. Then this map also is a homomorphism from the unit circle to itself. But if we choose some suitable t such that the rotation number is the golden mean. Then this map also is analytic diffeomorphism defined from the unit circle to itself. And if the rotation number is nice, then this map has a Herman ring surrounding the unit circle. And it is a Herman ring and cannot be a Siegel disk because the 0 and the infinity are insertion is a singular point of A. So this is the second example. And the third example is also a Blaski product of degree 5. And here we add the parameter A here. The A is choosing such that this map has a fixed parabolic point here with rotation number like 3/7, and it would also require the rotation number and the unit circle is the golden mean. Then this map has unit circle surrounding has a Herman ring surrounding the unit circle. Okay, this is the first method constructing Herman rings by studying the circle diffeomorphism by Arnold and Herman. And this Herman rings has a symmetry tricks about the unit circle because they are constructed by studying the circle diffeomorphism, and these maps can be written as Blaski products. And the second method is due to Shishikura by quasi-conformal surgery and turning the Siegel disk to Herman rings. So we first need to study some properties of Siegel disk. Suppose F is a non-linear holomorphic gene. It has an irrational fixed point at the origin, and the rotation number alpha is alpha. A very remarkable theorem due to Siegel is that if alpha belongs to Diophant-2 number, then F has a Siegel disk at 0. And then later on, Bruno extend the Siegel's result to the all Bruno type. And actually, in the 1980s, the Doadi has a conjecture. It says that if this map has a Siegel disk, then alpha belongs to Bruno type. If a Siegel disk has rotation number not in the Bruno type, this Siegel disk is called exotic. This is a strange Siegel disk. And until today, I think there is no exotic Siegel disk. And all the evidence suggests that this conjecture is true. And the original statement for this conjecture is for rational map, but I think this conjecture can be stated for more general holomorphic functions. In the later of 1980s, Yorkos proved that this conjecture holds for quadratic polynomials. And I think his proof depends essentially on the fact that the quadratic polynomial has only one critical point. And this conjecture is still open even for cubic polynomials today. So it, of course, it's open for higher degree polynomial and high degree rational maps and other anti-functions, the meromorphic functions. But some progress has have been made by Prismarko, Jie, Okuyama, and Manav and Shaki. And as far as I know, all the proofs are dependent on your course result. And they have some restrictions on the forward orbit of critical points. Oh, sorry, I should say Shihadi, his result does not depend on Yoko's result, because his results relies on the inner Shishikura's parabolic renormalization. And but I think this the result of them depend on this result, but the Shihadi's result does not depend on this result. He also gives an independent proof of this result for the high type numbers of. Okay, let's recall Shishikura's construction by quasi-conformal surgery. He starts with a rational map F naught. It has a p periodic Siegel disk from S1 to S2 and to SP, and then go back to S1. And he can choose a sequence of periodic caps, gamma 1, gamma 2, and gamma p. Then he also finds some maps F1, F2, and Fp such that the composition of these p maps also has a Siegel disk. Suppose this cycle Siegel disk has a rotation number theta. He chooses this map such then no composition has a Siegel disk of rotation number minus theta. Then he pastes this p Riemann ball to Riemann sphere to along nail caps in the Siegel disks to obtain a quasi-regular map like this, to paste the dynamics outside this disk, and then paste here. He also obtain a Riemann sphere, and there is a quasi-regular map big F. Then he chooses some. He can prove there exists an invariant complex structure of big F. Then he can obtain a rational map realizing the big F such that the resulting rational map has a cycle of Herman rings with rotation number theta. And the rotation number is the same as the original map F naught. So from Shishikura's proof, he also stated a result. If we know there is a rational map has a Siegel disk of rotation number theta, then there must exist another rational map G, such that G has a Herman ring of rotation number theta. And the inverse is also true. So from Shishikura's construction, there is a very deep connection between the Siegel disk and the Herman rings. So this surgery has some flexibility. It means that the Herman rings need not to be symmetric about some cycles. But it also has a problem, is because if a Herman ring has no symmetries, then it is hard to find its formulas. For Arnold and Herman's construction, we know the formulas can be written as a Blaski product, and one can find the formulas, and we can find the parameters. But from Shishikura's quasi-conformal surgery, we have a lot of Herman rings, but we don't know what are the formulas of them. And in 1980s, Shishikura noticed this problem, and he tried to find some formulas of the rational maps containing non-symmetric Herman rings. And in his paper, he said the construction not only assumes us the existence of Herman rings of order P, actually periodic P, but also suggests that if gamma 1 is choosing sufficiently close to the center of S1. S1 is the Siegel disk. That means if this cap is very close to the center of the Siegel disk, then the resulting rational map big F will be very close to the original rational map F0 outside a neighborhood of the centers. That means if gamma 1 is very close to the center, then from this surgery he can orbit a rational map big F. Actually, this big F is quite irregular, and he also think this is also a rational map. He identified this these two sets, and he identified this is a rational map. So if the cap before surgery is very close to the center, then it is expected the resulting rational map is very close to the original rational map outside a neighborhood of the centers of the Siegel disk. So he think if the f0 is equal to the quadratic polynomial c squared plus c naught with periodic 2, and expected the resulting rational map has the following form: c squared times c minus a over c minus b plus c, and the c is very close to c naught, and the a and the b are very close to the center of the Siegel disk, and then the big F is very close to F0 outside a neighborhood of 0. And he also did some numerical experiments by trial and error method. He find some parameters C0, A, B, and C, and he can use these parameters to draw pictures of the Herman rings of the periodic 2. But we know the Herman rings are accumulated by the forward orbit of critical points. So he only drew the orbit of critical points, a critical orbit of the maps. This is the critical orbit of the originally quadratic polynomial, which has a Siegel disk of periodic 2. Then for the resulting rational map big F, then he can also draw the 2 critical orbits, and we can see this critical orbits accumulated the boundary of this Herman rings, and he also draws 2 periodic caps in the Herman rings. And this picture was drawn by me, and I draw the whole junior set like this. And also draw some 2 inferent caps, 2 periodic caps in the Herman rings. So I think Shishikura produced such examples, and then he is not satisfied with these examples. So he actually raised the following question: please find an explicit form of a rational map which has a Herman ring of periodic 2 and draw its picture. And we can see why this question is not easy. The first one is we can show if a rational map has a Herman ring of periodic at least 2, then this Herman ring cannot contain any circle satisfying FP C equals to C. That means if a Herman ring has periodic 2 or more, then this Herman ring cannot contain the periodic circles. So it implies
geometric you don't use.
Sorry?
Jordan curve, of course.
So what do you mean by circle here?
Circle, it means round circle, round circle.
Geometric circle.
Round circle, yes. Originate circle, yes, round circle, not the topological circle, round circle.
No, Herman rings. Built.
Yes. So the idea is the proof idea is very simple. If we can suppose if C equals to the unit circle by holomorphic coordinate transformation, and suppose F P maps the unit circle to itself, then we define a new map, big Z. It defined as if Z equals to if Z belongs to the outside of the unit disk, then we write it. Then we define big Z F equals to FP. If Z is in the unit disk, then we define big F to its symmetric. And it is easy to see big F is also a rational map, and is also a rational map, and it coincides with FP in the outside of the unit disk. But for this map, if F has if the originally small f has a stack of Herman rings A1, A2, AP, then this big F will have two circles of Herman rings A1, A2, AP, and tau A1, tau A2, tau AP. The tau is this map is the inversion about the unit circle 1 over conjugate Z. So this it has two circles of Herman rings, and these two circles of Herman rings coincides at the Fadot component containing unit circle, and this is a contradiction. So we know this periodic Herman rings cannot contain any circle, any periodic circle. So this suggests us if we want to find formulas of rational maps have a Herman rings of high period, then it is hard by studying analytic circle diffeomorphism. So we have only one choice. We need to use quasi-conformal surgery. And our first result is like this. Suppose theta is a Bernoulli number and p is an integer. Then there exists a naught. It is greater or equal to 3, such that for any a greater than a naught, there are two numbers b and u. U depends on a and b, such that the FAB equals to u z squared times z minus a over 1 minus az plus b. Such that this map has a p circle of Herman rings of rotation number theta and a super attracting p circle containing 0. In particular, if p equals to 2, then u can be written as this formula. It is can be written as the formula of a and b. And actually, this we can see this formula. This is a number. This is independent of z, and then this place looks very similar to the Blaski product, because z is real. Here we require a is real. So this is a cubic Blaski product and times parameter u. And if we take a derivative, and we will have 4 critical points, and the 4 critical points is just like this Blaski product. It has a critical point at 0, a critical point at infinity, and then it has other 2 critical points which are symmetric about the unit circle.
Question.
Yes.
So here A naught depends on theta and P.
You mean A?
A0 doesn't depend on theta and P.
That is a very good question. Actually, I think it is independent of P, but I don't know is it independent or dependent on P, because I think it depends on P, and or actually I know it depends on theta, but I don't know if it is dependent on P. I think it is dependent on theta, because if the periodic is 1, if the periodic is 1, if P equals to 1, then A naught depends on theta. Then also depends on theta.
I think it is a little bit misleading to take A0 big and to multiply. I would rather write that we have something less than 1/3 and to inverse 1 minus. I mean, then we will have Z divided by something close to Z, and then we see indeed that we can have degree 1 on the circle. I just suggested to in this homography to divide numerator and denominator by A. Then it will be better visible that we have Z multiplied by something close to 1 over Z, which gives a chance.
I see. Yeah, I see. What you mean.
Better way of writing this. Again, I suggest that A is close to 0, not big.
No, A couldn't be close to 0. A should be very large.
No, but I suggest the same what you wrote, but just divide in your formula the numerator and denominator by A. And then you have the same formula, but instead of multiplying by this homography, you just divide by the homography when you reverse numerator and denominator. The same what you told, but different way of writing.
Yes, I think
my understanding is, I learned it maybe from Herman paper, that a way of construction is that you just take Z square, but you want to divide by Z, then you obtain degree 1. You have Z square divided by Z. If you want to perturb it, you perturb it by a homography. Just divide it by homography, which is close to Z. Divide, not multiply. You get it if you replace in this formula, if you in this formula divide numerator and denominator by your A, you obtain instead of A, you obtain 1 over A, which is then close to 0 if your A is close to infinity.
I see. Yes, I also saw the formula as you said in some papers like that. Right?
It's perfectly okay, but I just wanted to say that I'm somehow accustomed to look differently at this.
Yes. I see. Yes. But yes. In the right as Z times something like this. But
Z times 1, but then you perturb this constant 1 by ratio of by homography.
Okay. Yes. Okay. So yes, and I think the A naught depends on theta. But here we find the formula for actually also for some numerical experiment to find the A naught. if the A naught is given, then we only need to find the parameter B in session because the U depends on A and B. If A is given, and the B was choosing, then U is determined by an equation because the zero, the origin is a super attracting p-cycle. So such as if the periodic is 2, then U can be written as the formula of A and B. And how to find this formula? And there are two main steps. The first one is by turning p-cycle Siegel disk to p-cycle Herman rings, and the idea is similar to Shishikura's procedure. And the second one is to deformations of Herman rings, and the deformation was including the changing the conformal modulus and the twisting the Herman ring. Twisting means that we can change the relative position of two boundary components of Herman rings. And how to use the deformation of Herman rings, and actually it was proved by Brown and Virginia in their book. And the result states that if F is a rational map having a Herman ring of modulus of M, and suppose for all K, Fk maps each component of F minus Ka to A with degree 1, then there exists an analytic family of rational maps F lambda parameterized by punctured unit disk, such that F is conformally conjugate to the original map, such that F is conformally conjugated to F lambda naught. F is the original map. This is a family of map. And F lambda has a Herman ring of modulus like this. And this we can see the modulus can change, can verify from 0 to infinity. So this is a property. And the last property is F and F lambda are quasi-conformally conjugate, and the conjugate is conformal outside the ground orbit of the Herman ring A. So from this theorem, we know that if F has a Herman ring, then we can change, then we can obtain an analytical family containing this rational map F, such that these families, or every map in this family has a Herman ring, and the Herman ring varies, and the modulus varies continuous, and because it is parameterized by a complex parameter, actually the lambda from this lambda we can obtain some additional information about the relative position of the two boundary components of Herman rings. So the surgery, this theorem is also proved by quasi-conformal surgery, and one real parameter used to change the conformal modulus, and another real parameter used to change the relative position of the boundary components. So these two real parameters from these two real parameters, one can obtain a complex parameter lambda. And from this theorem, we can string the resulting cubic rational map F in our surgery. Here, if we turn in the p-cycle Siegel disk to p-cycle Herman rings, we will obtain a cubic rational map like this. And from this rational map, we see now 4 parameters, mu, alpha, beta, and omega. And then from the Browner-Vaginus theorem, we can cancel a parameter, because this surgery allows us to deform the map in the parameter space. If we deform the map, then we can choose some suitable parameter such that the alpha and the omega equals to each other. So we obtain map has this form: u z squared times u minus a times over 1 minus az plus b. Of course, just the Felix suggested I should write this formula more reasonably in the time in the okay. And so from this we can have a picture of okay, yes.
So this step, the last step, is just to change this first formula from z to the second. So after the first step, you obtain this z square z minus alpha, right?
Yes. From first step, we obtain this map. Yes. Yes, because okay. Yes, I think I forgot to mention because I need to say what is the original map before surgery. The original map is a quadratic polynomial, has a p-circle Siegel disk. The original map it has it's a quadratic polynomial, has a Siegel disks of periodic p. Then we performed quadratic surgery just as Shishikura, and then we obtain a map, a cubic rational map like this. And this map has 4 critical points: one at the origin, and another at the infinity, and then there are other two critical points which are associated to the bonds to the Herman rings, and the zero will be mapped to back. 0 is a critical point will map back by p steps. And then from this formula and the this theorem, we can obtain this formula and to put the alpha and the omega the same. And if they're the same, we choose the a equals to 4, and this actually in this case we find this formula by also numerical experiment, because we need to show the a1 a0 is less than 4. Then we can find some a greater than a0. Here we choose a equals to 4. Here in this example we choose a4 and p equals to 2. P equals to 2, and the u, we know the formula of u, and if we know a0, is less, actually we conjecture in some case a0 equals to 3, but it shouldn't be a for all theta. This depends on theta, but I don't check if it depends on p. Okay, it's from this periodic for p equals to 2, and we can obtain this formula like this, and then from this formula we can see we only need to find one parameter b. So we can find the parameter b in the parameter space such that the rotation number is the golden mean, and then we can draw a picture like this. It has 2 cycles of Herman rings. And how to find the parameter b? And there is a method by studying the parameter space, we first draw the parameter space of F4B. In this case, P is equal to 2. And from this, we can actually this set corresponding to the Herman ring parameters and also some other parameters. We can find the Herman ring parameters on this set. If we zoom the parameter space near the bifurcation locus and zoom, we can find a more precise parameter. And this point corresponding to the golden mean parameter, golden mean rotation number. If you give another rotation number, you can zoom at another place to find the parameter B. Okay, we can also find for P equals to 3, we can also draw some pictures containing a Herman ring of periodic 3. But in this case, we cannot obtain a good formula U of B as the case P equals to 2, because we cannot write the U as a good formula as B, but we can solve an equation to obtain the values of B and the U. We can first find B, and the U is determined by B and this parameter A. Okay, now let's go to the meromorphic case. We first mention some results. The standard family of statistical homomorphism, FAT. This can be seen as perturbation of the translation theta by t, and this is the perturbation term. This statistical homomorphism induced the complex vacation, big AAT, like this, and as we mentioned as before, it write as e to 2 pi itz times e to a over 2 times z minus 1 over z. This map maps the unit circle to itself by homomorphism, and this is a transcendental holomorphic maps defined from punctured complex plane to itself. Then there are some results about this family. The Herman, but the Herman rings exist in this family, as we have also drawing a picture about this family. And the Baker and the Dominguez prove that any transcendental holomorphic function defined from the punctures to itself does not have a p-cycle of Herman rings with p at least 2. Actually, they proved a more stronger result, and the more stronger result can imply this map cannot have p-cycle of Herman rings of p greater or equal to 2. And for this family containing Herman rings, and the Bill, Virginia, Nigeria, Henriksen, and others published a lot of papers on the Herman rings of this family. Now we turn to the Herman rings of transcendental meromorphic functions. The first example of Herman rings in transcendental meromorphic functions defined.
May I make a remark on the previous picture? Could you?
Yes.
So maybe not everybody knows that the first proof that trigonometric polynomial, the bounded number of periodic orbits, was by Misha Jakobson 40 years ago, maybe, or 30, just by complexification like this. And then you obtain finite number of critical points, and periodic orbits must be served. This was fantastic half of page proof. So this is. No, I just wanted to pay your attention that we have here an example of trigonometric polynomial.
To find an example. Okay.
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 Go on. Just so I wanted to mention Jakobson here.
Oh, Jakobson. Okay. Okay. Thank you. Okay. Let's look at the Herman's in transcendental meromorphic functions. And the first example of Herman's in transcendental meromorphic function was constructed by Zheng. He also used a quasi-conformal surgery from an transcendental anti-functions to perform surgery to orbital meromorphic functions such that it has Herman's. From Siegel disk to Herman's, yes. And then Domi gas and the vagina independently give some examples of Herman's of transcendental meromorphic functions in a variety of arrangements. The first example was constructed by Zheng, and in some places they said independently they also give some invariant, and they also give some examples of Herman's. But those Herman's has a variety of arrangements. And in 2012, and the Vagina and the Peter proved the existence of Herman's of any given periodic root in transcendental meromorphic functions, also by quasi-conformal surgery. And recently, Russia proved the existence of Herman's in elliptic functions. This is a very special transcendental meromorphic functions. Double periodic meromorphic functions, and she can also prove the Herman's can exist in this kind of meromorphic functions, but it's very hard to find a picture of to draw a picture of a Herman in this family. Even in periodic one, it's very hard to draw a picture. Not a picture, because it is hard to find a formula. So it is hard to find the parameters. So it is difficult to draw pictures of Herman's. As before, we can also prove if U is a Herman of a transcendental meromorphic function of periodic P. Here, P is ordered to be 1. Then U cannot contain any circle, the alginate circle, satisfying FPC equals to C. Recorded in the rational case, we required P is greater or equal to 2, but in the transcendental meromorphic function, meromorphic case, the P is ordered to be 1. That means for any Herman's of transcendental meromorphic functions, the Herman cannot contain any circle, any periodic circle. The proof is the same as the rational case. Because if it has a periodic, it is a fixed, if the Herman is fixed, then you can use a symmetric analytic extension. Then you will obtain a singularity at the essential singularity and the finite complex plane, which is a contradiction because the map here is a transcendental meromorphic function defined on the complex plane. It only has the poles in the complex plane, but it cannot have essential singulars in the complex plane. And so Shishikura's question can be also asked for transcendental meromorphic function to find the explicit form of transcendental meromorphic functions, which has a Herman ring of periodical 1 or 2 and draw its picture. And actually for periodical 1, the dominant gas and the vagina has find an example. They also use quasi-conformal surgery to paste an invariant subdisk of a quadratic Siegel disk. To paste the complement of an invariant subdisk of a quadratic Siegel disk to 0 of this map. Then they get a meromorphic function like this. So for this map, this map has a Herman ring of periodic 1 by choosing suitable parameters A and B. For P equals to 2, then we have following result. If theta equals to B equals to the Bernoulli type, and then there exists kappa such that the EZ has a 2 periodic Siegel disk whose notation number is theta. The this family has a 2 periodic Siegel point. Then from this map, we can use quasi-conformal surgery to produce a meromorphic functions such that it has a 2 cycle of Herman rings of rotation number theta, and theta is the Bernoulli type, and the quasi-conformal surgery, and you can use the standard method to construct the Herman rings from Siegel disk, and then after stressing the resulting quasi-regular map, you will obtain meromorphic function. What you need to do is to verify the resulting meromorphic function has this form. And they need to study some because most of the properties of the original map have not been changed near the infinity. So you can use some. You can say you can conclude the resulting meromorphic functions has this form. You only need to say it has a study is critical points, study is poles, and then you can find this formula. In the pictures of Herman rings in transcendental cases like this, you can, for this family, you can choose some suitable A and B such that it has fixed Herman ring like this, and the other Fadot components reiterated eventually onto this green part. And for periodic 2, you can choose some parameter A and suitable B such that it has a periodic Herman rings like this. Actually, we can also, because our result just produce the periodic 2 Herman rings, this result. Actually, we can produce any periodic Herman rings, produce any periodic Herman rings. Why this is different from the rational case? Because of this proposition, we can see for any theta belongs to Bernoulli type and the P is underneath the 1, then there exists the lambda such that E lambda equals to lambda times Z squared e to the Z has a P cycle of Siegel disk with rotation number theta. And for rational case, this result, we don't need to prove this result, the corresponding result. For rational case, the model, the before surgery is a quadratic polynomial. In that case, we only need to begin with the quadratic polynomial Z squared plus C. squared plus c can produce a p cycle of Siegel disk with any rotation number in Bernoulli type. But for the n-type functions, we need to find a family such that it can produce a p cycle of Siegel disk, and also with any rotation number in Bernoulli type. So this is the difference between the transcendental meromorphic case and the rational case. In rational case, we don't need such a similar proposition, but in transcendental meromorphic case, we need to use this result. Assuming this result, we can use the quasi-conformal surgery to produce a family like this, such that it has a p cycle of Herman rings of rotation number theta in Bernoulli type, and a super attracting p cycle which is different from 0. We also need to use produce a super attracting p cycle which is different from 0, because for this family the 0 is fixed. So in our example, because for this map the 0 is fixed, is a super attracting fixed point, and it has a p cycle Siegel disk, and the center of the Siegel disks are different from the origin. So after surgery, the 0 will be corresponding to 0 here, and the p cycle of Siegel disk corresponding to p cycle of Herman rings, which are the origin does not belong to the Herman rings, the neighborhood of the Herman rings, and we produce a super attracting p cycle which is different from the origin. This is the parameter space of the model map E lambda equals to lambda g squared EG. We can see a Mandelbrot-like set in the parameter space. If we can prove the existence of the Mandelbrot set, then we can use Doherty and Haber's polynomial-like theorem to prove this family can produce produce the p cycle of a Siegel disk of any rotation number in Bernoulli type. So the idea is to prove there is a Mandelbrot-like set in the parameter plane of this family, and I think this definition is standard. We only need we can read this quickly. And the FUV is a polynomial-like mapping if the U is compactly contained in V, and F is defined from U to the V is a holomorphic proper mapping of degree D, and the Julian set is KF defined as the point G which are whose iterates are stated in U forever. The Julian set is the boundary of the field in Julian set, and this triple is called the quadratic-like if the degree is 2. And we can also induce the family of polynomial-like mappings. This family is parameterized by the parameter lambda. It is called the family of polynomial mappings if the boundary of U lambda and the V lambda vary continuously as lambda varies, and this map lambda g to f lambda g depends holomorphically on both lambda and g. Then if it satisfies these two conditions, then this family is called a holomorphic family of polynomial-like mappings. Doherty-Haber's result says that if there is a holomorphic family of quadratic polynomial-like mappings, and suppose there is a closed disk D contained in this big lambda, such that the unit critical point, because it's a quadratic like, so this map has only one critical point, and with local degree 2. For the unique critical point W omega lambda in U lambda, F lambda omega lambda minus omega lambda tends around 0 only once, as lambda tends around the boundary once. And the critical value F lambda omega lambda belongs to the annulus for every lambda moves on the boundary of D. If this family satisfies these two conditions, then there is a subset M, which is homomorphic to the standard multiple set, map lambda equals to C lambda, where M is given by this set. The orbit of the critical point is always in U lambda for all and for all A. Moreover, for each lambda, F lambda, the restriction of F lambda and U lambda is topologically conjugate to the quadratic polynomial and their corresponding field in junior sets. This is the Doherty-Haber's stressing theorem. So in our case, for this family, we can find the explicit definition of the big lambda and the D. The big lambda is a disk minus the positive for real line, and the D is a subset of lambda. It is I think it is like a sector. It's like a sector, but it is compacted contained in big lambda. If we choose lambda and the D like this, then we can obtain a holomorphic family of quadratic-like mappings. It satisfies these following two conditions. For these two conditions, then we can obtain a multiple-like set in the interval of D, such that the male coordinate of harmonic components has periodic 1. So to prove this lemma, the key point is to verify these two conditions. We need to have first we need to have quadratic-like mappings, and then we need to verify it is a holomorphic family of quadratic-like mappings. First, we verify it is quadratic-like mapping. And we take the pre-image of positive line under this map, we can obtain these curves. And then we choose a very big disk. And there is, I should say it is an annulus. The annulus minus the positive line, and then we obtain a simply connected domain. Then we take a pre-image, we obtain a domain like this, which is compacted contained in the original U lambda. This is U lambda. U lambda, and this is V lambda. V lambda is defined like this. It is an annulus defined by the positive for real line, and V lambda depends on lambda. And then you take a pre-image, you obtain several pre-images, but you choose a suitable pre-image here, and they can prove the pre-image is compacted contained in this domain V lambda. We call this shadow part the U lambda. Then E lambda U lambda, V lambda is a holomorphic family of polynomial-like maps. Holomorphic family of quadratic-like mappings. Okay, from this from just the result, we know we can obtain the family of meromorphic transcendental meromorphic functions with p-periodic Herman rings of any given rotation number in Bernoulli type. And actually, after our paper submitted to arXiv, and then NASA write an email to me, said he had this result with Dex lecture. They proved for any theta equals to B and P, there exists kappa such that the exponential family contains a p-cycle of a Siegel disk with rotation number theta. So if we have this result, then we can produce the family of transcendental meromorphic functions such that they have a p-cycle of Herman rings and the super attractive p-cycle. But the difference is the Herman ring construct in this case is the Herman ring. I should say sometimes it is unbounded, but not always unbounded. Sometimes it's unbounded. So there is sometimes, because if the rotation number is Herman type, then the Siegel disk of this map is unbounded in the complex plane. Then the Herman ring after surgery should also be unbounded. But if there exists some theta such that the Siegel disk of this map is bounded, so we couldn't say it has a p-cycle of unbounded. Sometimes, as here is unbounded. But we know in some simple case, if the rotation number is of bounded type, then even the rotation number is bounded type, it is hard to draw a nice picture, because if the Siegel disk is unbounded or the Herman ring is unbounded, the picture is very hard to draw. But in our case, if the Siegel disk and Herman rings are bounded, then the picture is easy to draw. Now we can show some more examples of Herman rings. The first is the Herman rings of internest case. What it means? It means the three critical points lies on the boundary of different Herman rings in the same cycle. Suppose it has the Herman ring has the Herman rings has periodic 2, A1 and A2. Then in the previous examples, our critical points are associated to, or in a simple case, if the rotation number is bounded type, if the rotation number is bounded type, then the two critical points aligns on the boundary of the same Herman ring. The two critical points aligns on the same Herman ring. But actually, one can construct the Herman rings such that one Herman ring has the boundary of one Herman ring has only one critical point. This is called the internest case. And the second is about the nested Herman ring. What is the nested Herman ring? We can first see what is non-nested Herman ring. Non-nested Herman rings, the outer boundary maps to the outer boundary, and the interior boundary maps to the interior boundary. And all the results we stated before is the non-nested Herman rings. And the nested Herman ring means the map maps the outer boundary to the interior, and the interboundary maps to the outside, and the integral map to outside map to integral, and this is non-nested, this is nested. And we can also construct some nested Herman rings based on Shishikura's surgery. For any theta, there exists a pair RT such that HRT has a two cycle of nested Herman ring of rotation number theta. This is also Blaski product of degree 4. And we can draw this picture like this. This Herman ring is very different from previous example, because in previous examples, the Herman rings are surrounding the unit circle, but in this example, the unit circle is contained in junior set. This is the unit circle. And the Herman ring is very small. We couldn't see it. It is this is not Herman ring. This is the pre-image of Herman ring. The Herman ring is here. And what is another Herman ring? Because this Herman ring has period 2. Another Herman ring is the symmetric image about the unit circle of this green annulus. The symmetric image of this green annulus is another Herman ring, and then they form an two circle Herman rings. Okay, this is the examples of Herman rings, and then finally, I would like to state some questions. Actually, some questions on Herman rings can be reduced to notes on Siegel disk. For example, the topological characterization, the self-similarity of the boundaries of the Herman rings at the critical points can be proved. It was proved by Gina and Henriksen by using the McMahon's result on the self-similarity of the bounded type Siegel disks at the critical points. I think the first question is find the formulas and draw pictures of more complicated configurations of p cycle of Herman rings. For example, the 3 cycle of nested Herman rings. We can only produce examples of 2 cycle of nested Herman rings. If the Herman rings are nested, very complicated, the formulas is very hard to find. But such kind of Herman rings are were granted by Mitsubishi Shishikura. The second question is about when a meromorphic functions have a Herman ring or does not have do not have a Herman ring, because we know the Herman ring is hard to find because it has no associated periodic points. For other periodic Fadou components, super attracting, geometric attracting, parabolic, and Siegel disk, they all have an associated periodic point. But for Herman rings, it does not have associated critical, associated periodic point. So it's difficult to find Herman rings, and some results have been obtained by Mitsubishi and Mino and other people. And the last question is like this: does there exist a rational map with exactly 3 critical values having a Herman ring? The answer is if the critical values is 2, has only 2 critical values, then by the result of Shishikura and the Mino, the result is negative. But we know from by Herman, the answer is yes if the critical values, the number of the critical values is 4, because we can. Herman has produced the cubic plastic products with the Herman rings. And the cubic plastic products has exactly 4 critical values. So later question is to find does there exist a rational map with 3 critical values such that it has a Herman ring? I think the answer is negative, but I don't know how to prove. Okay, thank you for your attention.
Thank you.
Questions from the audience?
Very impressive.
Can I ask a question?
Go ahead, David.
So I wanted to ask, maybe I didn't pay attention. Your examples of meromorphic functions with Herman rings, do they have infinitely many poles, or does it depend? Are there examples with only finitely many poles with these Herman rings?
Sorry, could you speak that again?
Sorry. Your examples of meromorphic functions with explicit formulas with Herman rings, do they have finitely many poles or infinitely many poles?
Finally, many poles, yes, finally.
Yes.
Yes, but I think maybe there exists. I think the Zheng he produced an example of transcendental meromorphic functions which has infinitely many poles. He started with anti-functions with infinitely many Siegel disks. Infinitely many Siegel disks, then by quasi-surgery he can produce transcendental meromorphic functions infinitely many Herman rings. And then those map has infinitely many poles.
I was wondering, like in the other direction, whether there is a restriction on the period depending on the number of poles. Like if there are very few poles, just 1 pole or 2 poles, whether you can still get all the periods or something. I don't know.
Okay, that's a good question. I think okay, I don't know at this moment. I think
it's like if you only have 1 pole, maybe it's closer to entire functions in a sense. I don't know.
Yes, because we start with very nice anti-functions before the surgery. So
Can I ask another question, Artyom?
Sure, yes.
Okay. So I also wanted to ask about, you said that functions that are holomorphic in C star, they can have a Herman ring, right? But it needs to be very special because it needs to separate 0 and infinity, and it needs to be invariant, of course, because there can only be one of these doubly connected tattoo components in that case. And I wanted to ask if you thought about the case where the function is meromorphic in C star. So both 0 and infinity are essential singularities, but you allow for some number of poles. Do you know whether in this case you still have this type of restriction, whether Herman rings need to be separating the 2 essential singularities, or they can be anywhere, or what the period can be?
Okay. I get your question. I think I don't think this question before, but I know this question is very close to this question. When meromorphic functions have a Herman ring, it depends on the distribution of the poles and it's close to your question. Sometimes the periodic of Herman rings and depends on the distribution of the poles, I think, but I don't have explicit description.
Okay.
Thank you.
Any more questions?
What I said about trigonometric polynomials didn't make sense because you are interested in maps which on the circle are topological rotations. And I mentioned that the bound for periodic orbits on the unit circle for big perturbations which have folds on the circle itself. Then it makes sense to estimate number of periodic orbits. So again, my comment didn't make sense.
Yes, I think yes.
Your parameters that sign your sign is small, not big.
Yeah. This is a very good comment. Yes. It should be more. Should be find the parameter, estimate the range of the parameters.
Yeah.
Yeah.
You find interesting dynamics outside this circle. The circle is in the Herman ring, or sometimes yes.
Cycle.
This is for your maps you are interested in, that this circle is in the Herman ring.
Yeah, that does not exist a circle in Herman ring. Yes, circle. I should mention what the circle is.
Yeah.
Okay. Yes. Good for a comment. Okay, but the newspaper has been published online today, so I don't have choice. Have chance to, but maybe I should make this comment in the archive version.
Okay.
Thank you.
Any more questions or comments? If not, let's thank you.
Thank you.
Thank you.
Good lunch or dinner, or depending which time zone. You have evening, China.
So you will go to have lunch now?
Yeah.
Okay. I think I need to go to sleep now. It's about 9 o'clock in the about 9 o'clock in the evening in China.